All right, let's quickly take a look at the basics of Newton's second law. So, Newton's second law tells us that if you have a net force acting on an object, it causes that mass to accelerate. Now, if we look at the units here, right, mass is measured in kilograms, acceleration is measured in meters per second squared. So, kilograms times meters per second squared gives us that unit of newtons, right? So, that's where this comes from. So basically, if you have an imbalanced force, a net force, your mass will accelerate. So just remember that in math, if you're looking at the Greek letter sigma, sigma just means, right, the sum of all, right? So sigma F would be the sum of all forces, right? So sigma F, sum of all forces, right, which means your net force. So what do we mean by that? Well, take for instance, let's say we've got a scenario where you've got an object that's being dragged along by some applied force. Okay, well, it's got the normal force, it's got the gravitational force, it's moving to the right, and let's say that there is some amount of frictional force. Now, notice I drew this frictional force vector much smaller than the applied force vector. So what we're saying is that the applied force is greater than the frictional force, right? Whereas these two are, I tried to draw them roughly identical. Your normal force and your gravitational force are equal. So in the vertical, this guy is in equilibrium. But in the horizontal, you have an imbalance of the forces, so you have a net force. So if we were to look at the net force in this situation, well, your net force would be your applied force minus your frictional force. Right? So whatever value this has minus your frictional force gives you your overall net force. And that and the mass would determine the acceleration of the object. So let's take a look at how this would be applied in conjunction with kinematics. So in the notes, we've got example 4.6, racing down the runway. And so we're told a Boeing 737, a small short-range jet with a mass of 51,000 kilograms, sits at rest. The pilot turns the pair of jet engines to full throttle, and the thrust accelerates the plane down. After traveling 940 meters, the plane reaches its takeoff speed of 70 meters per second and leaves the ground. We want to know the thrust of each engine. All right, well, if we are dealing with forces, the first thing you want to do is always draw a free body diagram. All right, so this is our jet plane. It's moving down the runway this way. Let's see, it has a mass of 51,000 kilograms. So we'll just tack that over here. Mass equals 51,000 kilograms. We are given that it travels a distance of 940 meters. So we'll put x equals 940. We are also given, let's see, that its takeoff speed, so its final velocity, is 70 meters per second. And we want to know the thrust of each engine. So in this scenario, our free body, we'd have a normal force. We'd have a gravitational force. In the vertical, these guys are in equilibrium. Now we also have two thrust forces. So I'm going to call that Ft for thrust, Ft for thrust. Now, we're given no indication of any sort of drag force or frictional force, so we don't have to worry about that. But we want to know what each one of these individual forces is. Now, there's one other assumption we can make. A plane on a runway. The initial velocity is going to be 0. Alright, so if we want these forces, we've got a mass, but we're going to need to know What is the acceleration of that airplane? So that's our first goal here. We've got all of the kinematic values we need to find acceleration, so then we can use that combined with the mass to find our thrust. So if we take, let's see, v squared equals v naught squared plus 2ax, where v squared is 70 meters per second, v naught is 0, plus 2 times unknown times 940 meters. And we solve that out. So let's see, 70 squared divided by 2 divided by 940. And we get an acceleration of 2.61 meters per second squared. All right, so now if we look at our net force equation, our Newton's second law, that tells us that if you have an imbalanced force, masses accelerate. Well, our net force in this scenario is the sum of your two tension forces. Now again, we're adding these guys together because they go the same direction, right? In this case back here, we subtracted our forces because they were opposite directions, right? One is positive, one is negative. So if your forces go the same direction, right, they're both positive, they are added. So Ft plus Ft equals ma, right? Or 2Ft equals ma. So now I can plug everything in. So 2 times our unknown thrust force for each engine is equal to that 51,000 kilograms times our acceleration of 2.61 meters per second squared. So 2.61 times 51,000 divided by 2 gives us a thrust force for each engine of 66,463 newtons. Right, so your key when you're blending your kinematics and your force, or your net force equation, is always to find that missing acceleration if it's missing, right? Because acceleration is the bridge between your basic description of motion in kinematics and your explanation of why that acceleration exists, you know, in the net force equation. Now, I'll be uploading some problems that deal with some of these basic kinematic and net force equation mixtures up onto the Google Classroom here in just a bit. And also tomorrow or Thursday at the latest, I'll be uploading an in-depth look at two special forces, so weight and friction. And once we get more in depth with those two forces, then we'll see the problems start to kick it up a little bit. But yeah, I'll see you later.